smells travel, fuel burns, and you get drunk, all thanks to one thing. This is the chemical potential. We're going to see how the chemical potential powers your life, hides inside molecules, and is the real reason you should open the window after going number 2. There is an energy that we can physically use, and it's everywhere. But professors make it way too abstract, and most books make it so confusing. Energy required to add one particle to a system, energy released by adding a particle, a tendency, molar-free energy, work, causes voltage. Let's start from the basics. What is this energy and where does it come from? Molecules can potentially release or absorb energy in their bonds. Ions instead can potentially accept or donate electrons. All of these are studied in the branch called chemistry. So whenever you have chemical stuff, you have energy that can be potentially released and used. And since this energy is in chemical things, we call it chemical potential. And it's insanely important. It's the energy released from gasoline to move a piston, or by the ions moving in your phone to light up your screen. This energy allows us to do what scientists call useful work, which is anything that involves a directional movement. But let's make a real example. You're on E. You pull over to a gas station, put gasoline into your car, then make your way home. When you give gas, you get energy. But where does this energy come from? It comes from the chemical bonds in the gasoline molecules. They break and form new bonds as carbon dioxide and water. And the new bonds are more stable, they are stronger. So the molecules are going from a high energy state to a lower one. And the difference is precisely the energy that you can use to get a ticket. But here's the catch. Not all the energy goes into moving the wheels. Some of it gets lost, used to break the bonds and transform the chemical structure, entropy. So when gasoline burns, you get a big amount of energy from the bonds, but you lose some. And the difference is precisely the energy that you can physically use to run away from the cops. And this energy is called Gibbs free energy. Now, let's say we have hydrogen that releases the same amount of energy to move a piston as gasoline does. But in this case, we're going to need 21 moles of hydrogen instead of only 1 of gasoline to release the same amount of energy. So hydrogen can pack much less energy per mole compared to gasoline. But to communicate better with other scientists, we can use a shorter sentence. We can just say that hydrogen has less chemical potential than gasoline. But careful here, per mole, hydrogen can pack less energy. But if you compare equal mass, hydrogen can pack more energy. If you have a tank of hydrogen and a tank of gasoline with the same weight, because 1 kilogram of hydrogen contains 57 times more moles, hydrogen can pack 3 times more energy than 1 kilogram of gasoline. Imagine 2 rooms. In one, you push as many balloons as you possibly can, and you leave the other empty. Now you open the door. What do you think will happen? The balloons will start going to the empty room. It's like they feel pressure on their back and are pushed to the other room. So while squeezing them in the first room, they stored your energy, and then they released it after you open the door. Now, let's say you eat a lot of beans. The molecules in the beans are broken down by the enzymes in your intestines, releasing the energy you are going to use to walk to the toilet, where you'll unleash the methane molecules formed. You then create a chemical potential gradient, having the poison squeezed in a part of the house, thus having a higher chemical potential. So spontaneously, the molecules will spread, thus getting to a lower chemical potential. Now, let's get a different example. Take the battery in your phone. When it's fully charged, on one side, the anode, the electrons have a higher chemical potential. On the other side, the cathode, they have a lower chemical potential. So what happens when you use your phone, you're opening the gates, letting the electrons flow. Now, different materials have electrons with different amount of energies. And the energy you see on your screen depends on how many moles of those electrons your battery has, times the charge of 1 mole, times the energy that 1 electron can potentially give you, the electric potential. And if we divide the energy that you see on your screen by the moles of electrons, we get the chemical potential of those electrons. And we can thus compare it to other materials and decide which battery to use in which occasion. Don't confuse the sign of the electrode with the chemical potential. The anode is the negative electrode because its standard potential is lower. What does it mean? We always write the redox reaction in the reduction direction, so in the direction of getting electrons. And we measure the will of each material to get electrons compared to one standard material, the hydrogen. And we made a long chart. So the sign indicates the will of getting electrons. And if it's negative, it means that that material doesn't really want to get those electrons because its electrons have a higher chemical potential compared to ones of the hydrogen. But if instead we put it in contact with a material with an even more negative potential, so a material that not only doesn't want electrons, but if it can, it shoots them away. Now, the first material has a lower chemical potential compared to this one. So the electrons will flow to the material with lower chemical potential and higher standard potential, because this material is more willing to get electrons in compared to the one with higher chemical potential and lower standard potential. Now, what happens when you remove one electron from an atom? You get an ion. We can see the chemical potential like a sort of molecular pressure. Where there is a high concentration, there is a high chemical potential. So a higher molecular pressure, so more energy that can be potentially released. And ions are constantly trying to go where there is less of them. So how can we use them to do things? But more importantly, where do you find concentration gradients of ions? You find them in your brain. In your neurons, the outside is packed with sodium ions, while the concentration is less in the inside. This creates a gradient that is used by the neurons to fire. But we're missing something fundamental. Ions are charged, so this gradient creates also an electric imbalance. That's why for charged particles, the chemical potential becomes the electrochemical potential. Watch the next video to fully understand the electrochemical potential.